This is my second Chapter 11 reassessment. A playground ride consists of a uniform density disc of mass 300 kilograms and radius 2 meters mounted on a low friction axle. Starting from a distance of 5 meters from the disc, a child of mass 40 kilograms runs at 3 meters per second on a line tangential to the disc and jumps onto the outer edge of the disc. If the disc was initially at rest, how fast does it rotate just after the collision? So I defined the system as the disc plus the child and drew a picture here as this person running to get on to this is the disc. So the initial velocity here is 3 meters per second. It's 5 meters from here to here. The radius is 2 meters. This is the force of the axle. So I have the principle that we're going off of is that the angular momentum of A at A, the final, equals the initial angular momentum at A plus the net torque times change in time. And we know that the net torque is 0 because there's no outer forces on the system. So that means that the final angular momentum has to equal the initial angular momentum. So I've drawn here a second image showing that this is R, and this is the angle at which the tangential angle, I guess you could say, that we're going to measure to find the angular momentum. So we say that the initial initial angular momentum at Y is equal to the magnitude of R at A times the momentum times sine of that theta that I just showed you. And it can be rewritten as this. And we know that the radius is 2 meters times 40 kilograms, which is the mass of the child running onto it. That's how you get the momentum, times 3 meters per second is the initial velocity. And that gives you 240 kilograms times meters squared over seconds. So to get the final angular momentum at A on the y-plane, we know that it's going to equal the initial, so it has to equal 240 still. So we do I, the moment of inertia times W, which is omega, which is the angular velocity, plus R times M times V, which is the same thing as half of M times R squared times omega plus R times M times omega R. So when we add in our values, we get half of 300 kilograms times 2 meters squared times omega plus 40 kilograms times 2 meters squared times omega. We're solving for omega, the final angular velocity, and so we're going to do 240 divided by all of this, plug that into your calculator, and you get 0.316 radians over seconds.